Hi, we'll just wait for a few minutes and then start. So if you guys have any questions, you can ask me in the meantime. Okay, I guess we can start. I'll share my screen and then start. Okay, right. So last week we saw like, like we discussed about typecasting, right? Yeah. So last week we discussed about typecasting, where we take two examples of integer, float, and double. So let's say we have an integer I, we set it to 7, and by default, the behavior in modern systems is that it is integer is 32 bits, okay, or 4 bytes. Float is also 32 bits or 4 bytes, and double is 64 bits. As in, this is the space required to store integer, a float, or a double, like accordingly, correspondingly 32 or 64, whatever, right? Okay. So if you try and then we just print it, we see these values, right? And then we saw, what if we write or store, let's say d equals to I, where we are storing integer inside a double. Okay. So this is more of an implicit casting, right? Where you are promoting, sort of, as in you're storing uh, data which takes less bits to a uh, value which takes more bits. Okay. Now, these promotion usually doesn't uh, have any loss of precision, because you're just storing the same quantity in much larger like much larger storage, right? So you have extra bits. Anyway, you were representing something which, let's say, was in 32 bits, and you're storing the same thing in now 64 bits. So you anyway, if you are storing something anyway in 32 bits, and let's say that was accurate enough, or whatever the value itself was, it's not going to lose precision in 64, right? Okay, so this is an implicit cast where it converts an integer to a double. Okay. And the same thing, you can write it also this way, where explicitly mentioning double within brackets. This is an explicit cast where you're explicitly saying what you want to convert it to. Okay. Now, this is something, just to be clear, this is available in C++, where some data types can or will be implicitly casted if you do not mention them, and the compiler won't throw any error or anything. Other times, more or less, most of the other times, you have to explicitly cast your variable. Important thing to note again, when you're converting from one data type to other, it's all about if you're losing or precision or not. Okay, so sometimes one can um, be okay, or let's say the program itself is okay with losing precision in some of the portions of the code where it might not matter so much. So maybe then you can just convert one data type to other and then read off those values. But again, one has to be careful. Okay. So the next example is where you see I equals to int with d. Uh, Here we are explicitly converting double to an integer. Okay. So because double is, so for example, here double is 6.7 and it will be stored as an integer. So the decimal point values cannot be stored as an, like, is an integer, right? So those values get trimmed off. As in, the variable I has no idea of the fraction part of the number. Okay. So in this case, since we're converting a double, which is 64-bit, to a 32-bit number, we lose precision. So you lose precision of representing that fraction, and only the integral part, or 6, is only stored. Okay. This is some, you can even see the precision of your values. So maybe you can run that and see. Okay. So the final one, if we see, is just okay, that is 7 because it was already overwritten with few things. So like here we put 7 here, right? So maybe you can just comment these and then show the output. Okay, awesome. So D had 6.7, and then when we explicitly cast it as integer and store it to I, that prints 6. Okay. So sometimes the number can have lot more decimal points, and by default C++ has a limit to how much it shows by default. Okay, you can set that using standard precision, and have more digits shown accurately. Okay, like as in your output, the value itself is stored as much possible. Like if there is a number which will be stored till um, it's like if there's a number for 64 bits, how much ever it can store accurately, it will do it. But it's just that while printing, you sometimes don't see all the digits. So to set that, you can use standard precision. Okay. And the hierarchy of promotion or demotion, in a way, can think like this, where from left to right, the number of bits used to represent that number increases. And hence, when you try to convert a number from lower precision or lower bits to the higher bits, you have promotion, and then that can usually happen implicitly. You can do it explicitly also, but implicitly is also fine. When you go from the right to left, you lose precision, and usually you have to explicitly declare that. Okay. The next example we saw is this, where again we are storing some integer as I is 5. Okay. And we declare a pointer, which we're saying it is an integer pointer. Okay. And we're passing the address of I to it. Okay. So now the pointer has the address of I, okay, and and the value that the address stores is 5. So technically, I and P, in a way, you can think of it being the same thing, as in pointing to the same place. Okay. There's another C-style array just declared with A as 10, so it can hold 10 values, and all of them being integers. Okay. The other thing one can do is declare double, which let's say is 8.7, and another pointer, but this time a double pointer Q, storing the address of D. Okay. Next, we declare a void pointer, as in this pointer doesn't have any data type, as in it's a pointer which stores an address, but whatever the value the address has, we don't know its data type. Okay. So usually when we say integer pointer P, it means that there is a pointer, there is a address. So P is a pointer, right? So it will store an address. Now, whatever the address has, whatever the value it has, when we say integer, it means that the starting address till 4 bytes is what I will read. Okay. And that 4 bytes will give me some number. And that is an integer. Okay. So the data type of the value, whichever the pointer points to, is determined by this declaration. In case of void, that data type is just not known. Okay. So it can be actually anything, right? So yeah, so then we see an example where let's say we try to um, cast q equal to p. So q is a pointer of double type and p is a pointer. So an implicit casting between these two is not allowed. For pointers, you can't implicitly cast one to another. Okay. Again, p equal to q. It doesn't matter if you are thinking of integer being lower and double being higher and all that. For values, it is okay. But for pointers, there's a big difference because if you think about it, let's say let's say I have an integer pointer p, okay, and that pointer stores values in units of 4 bytes. Okay, and let's say, and for example, let's say there are 10 values like we have in A10, right? So let's say there are 10 values, so 40 bytes. Okay, now let's say I treat that pointer to be a double now. So the two values which took 4 bytes and 4 bytes from the starting, let's say, they will be treated as 8 bytes, okay, for my new number for the double, right? So now what happens is instead of 10 values, total is 40 bytes, right? And each, when for integer being 4 bytes, so you had 10 integers, okay. But if you take then the pointer to be double, now you have 5 values or 5 doubles. And if you think about it, you just combined 4 bytes and another 4 bytes, which used to represent two different numbers, into a new number. And that will, now your program will interpret that as a new number. And that can give you some all sorts of different values. Like what I'm trying to get at is treating a pointer as another pointer for values, let's say integer, custom data types, sorry, the inbuilt data types. So let's say integer, double and all. One has to be careful because you have to remember how numbers are actually stored. Okay, you can't expect uh, in a pointer which stores, let's say, integers to behave the exact same way when you convert it to double. You have to take care of the alignment. You have to take care of how each number in what units it was stored. Okay. The other thing is, let's go the other way. If a pointer was of double, okay, it used to use 8 bytes to represent one number. When you treat it as an integer, it breaks that 8 bytes into 4 bytes and 4 bytes, and you get two numbers. And each of them will be completely different from what the 8 byte used to represent. Right. To get more clarity, or if you guys are not familiar with how numbers are stored and how in bits and in computers, you can take a look at IEEE standard of floating point number representation for 32 bits and 64 bits to sort of get an idea as to how these numbers are stored. Okay. Nonetheless, people have done some clever bitwise manipulations just using these pointers where you recast into something else and then try to manipulate the bits. Okay. Again, that is also, if you guys are interested, you can take a look at the fast inverse square root algorithm that I mentioned last class. I won't discuss the algorithm, but if you guys are interested, you can just take a look online. Okay. So now let's say we explicitly cast the p pointer, which is an integer, to a double pointer and store it in Q. That is allowed because p itself has an address. Okay, we store something to it. And then when we cast it and then store it to Q, we can do that. We have an address. Now we're saying the program that we'll treat this new address, whatever this address has, as a double pointer now. Remember, initially it was just an integer. Okay, so it will be 4 bytes of data, and Q being double pointer will store that address, same address, and try and treat it as a double. But one has to be careful. When we try to print Q here, it's actually should give you segfault, but because we won't go out of the whole program's memory, we won't see the segfault always. But this should ideally give you a set point because you're accessing 8 bytes of data, whereas the address of P, okay, here, which is integer, right? That actually has allocated only 4 bytes to store the number 5. Okay, so accessing Q is not exactly recommended. So maybe I'll just comment this line. Similarly, you can also explicitly cast Q to which is double pointer, right? To P. But here you have to remember, okay, here we did have an address, so it is okay. But when you typecast pointers and initially when they're not pointing to anything, you can think of them to point to null. Okay, as in they're null pointers. They don't point to anything. Okay. Now here it's okay when you're trying to cast something and store, but if we hadn't stored anything, then that would give you errors. Okay, because a pointer doesn't, a null pointer, say at starting, doesn't have any address, and that you're trying to recast at whatever, recast is as integer, double or whatever, and then storing it to another pointer. Right? You can't do that because already the uh, existing pointer doesn't have anything. Okay. Next, if you see the next example where we say r equal to p, this is okay because r is a void pointer and p is of some data type, so integer, double or whatever. So you can store any pointer, actually any data type pointer to a void pointer because and there will be implicit casting. Okay, usually yes, you cannot store pointers as in there is no implicit casting between pointers. Only exception is the void pointer, which can have this because what we're saying to the program is I have an address and that I have a pointer which has an address, let's say um, of type integer or double or whatever. What we're saying is treat this address with no data type. I just give you the address and you store it in R, and that's all. That is absolutely perfectly valid because void pointer can just store the address and doesn't care about the data type it points to. Okay, so this is perfectly allowed, and the compiler won't throw errors, and you can write codes like this. The opposite is not allowed because, as in implicitly at least, because we uh, we knew our address, okay, and implicitly it can't just convert it to some other data type. You can explicitly treat it so and then store it as integer pointer or double pointer. Okay. The other thing is, so A, which uh, has 10 values, it's an array, right? Array of 10 integers. Okay. So 40 bytes of data. Now, the nice thing about this is A itself is a pointer pointing to the starting of this array. Okay, so these 10 values are contiguous in memory. So as in they are the first 4 bytes correspond to the first value. Then the next 4 bytes correspond to the next value and so on till 40 bytes. Okay, now the starting address of this array is given by this pointer A itself. Okay, so don't get confused. Well, we still write it as C style array where integer A 10. Okay, so you're declaring 10 values and this is an array, right? But don't forget that this A itself is an integer. A itself is a pointer. Okay, and P since is a pointer and can store an address, so P equal to A is allowed. The storing of integer pointer to another integer pointer. So here the integer pointer A, the address it has, we're storing the same thing to P. Again, implicitly it is allowed. But if you try to store A equal to P, as in whatever address P has to A, that will throw error because you declared a array. It already is the value A, the pointer A already points to some memory of contiguous data, right? And if you overwrite that address, then there is no pointer which is pointing to that address. So again, can lead to a lot of issues and then clearing memory also. So ideally, that is discouraged by the compiler and hence it throws an error. Okay. The other thing we see here is, let's say I want to loop over the values. Okay. So one thing is you use the brackets, okay, square brackets, a of I. So you access each of the elements. Remember, this operation is the dereference operator. So this is also a dereference operator, okay, which is essentially this thing. So I have a pointer A, so I add I to it. So it essentially does a pointer arithmetic, okay. So let's say the value, the pointer A is pointing to some address, okay. How much units do I have to move to access each element is determined by its data type. So A is integer. So each unit of 4 bytes will give me a new number. And that is implicitly determined by the operation, like the pointer operation. So you just have to worry about how many units you have to move, not the exact distance itself of each unit. That is automatically known because of the data type of the pointer. So a plus I, so this is pointer arithmetic. So we move the ith location from A. Okay, so for 0, it is a plus 0. So the first value, for I equals to 1, the second value, and so on. And when you apply the star, so this is the dereference operator, it accesses the value at that location. So a plus I becomes the ith value from the starting uh, a plus I becomes the ith location from the starting value A. And when you dereference it, you get the value at that location. Okay. So essentially these two are the same. And then when you access the value, you can overwrite it, you can access it to print it or do something else. Okay. Right. There was another question. So this is some snippet of the code which is I use it to explain some example. So for example, so let's say we have a function which returns a standard vector. Okay. And this is coming, let's say this comes from some external library or some other file or something. It returns something called a vector, which let's call it as the original vector. Okay. And let's define a class V. So this is what we write. Okay. And this class, okay, has uh, a member, which is the standard vector integer pointer V. Okay. So instead of storing the vector itself, we'll store a pointer of that vector. And when I say a pointer of that vector, I do not mean the pointer to the first location of that vector. What I'm doing is I'm storing the pointer to the object of that vector. A big difference, because when I access the first value of first data of the vector V, I can only access its elements. But when I have the pointer to the object, I have access to its data members also, which is the vector size, its capacity, all its data itself. Yeah, right. So when we say, let's say it's a vector of 50 values, I have access to those also and everything. Essentially, it is like accessing that vector, but without it being the member of the class. Okay. And let's say I make an object V, small v, okay, of this class capital B, and I access this vector V. So I can use dot, right, to access this member. So I'll write dot V equals to that ampersand func. So here,
Good of night.
the question. Okay. Uh, right. So what I'm doing here is I'm calling that function, and when I use the ampersand here, so this ampersand operator in this context means the address. So I take the address of the returned standard vector and store the address inside the V, which is the standard vector pointer. Okay. Next, what I can do is I can use the arrow operation, okay, to access. Yeah, so you can think of the arrow operation as the dereference operator and accessing the data member. Okay, so first of all, it will access the actual vector, okay, and then the data member, which is the data of the original vector here. And then using the bracket operation, you can access its original elements. So this operation essentially does this. So original vector dot data with I, or original vector with I, or original vector dot data plus I and dereferenced. So all of this access the same ith element, and the same thing you can do using the object of V also, using the object V and its member capital V. Okay. Same thing, you can access resize and all and so on. Okay. So this is a useful way in which you can even access pointers. So you can access objects which you don't have exactly access to, but you can access the pointer of that object and then access its uh, data members or functions, member functions, and so on. Okay. Any questions so far? Okay. I guess we can move on then. Okay, let's take more examples of this typecasting. As usual, we'll include the IOStream file to print stuff. Okay, let's define a class A, which let's say has public member integer I equals to 7. Okay, next we'll define a class B, which has public member, let's say double. Okay, so this is an integer I and a double, which is D. Okay, and that's it. Okay, so these are the two classes which have two public members, so we can access them uh, outside the class itself. Okay, we'll define now, write the main function. Okay, make an object of A, I'll call it small a. Make an object of B, we'll call it small b. Okay, then let's make a pointer of these classes. Okay, so this will have data type A point and pointer P. So pointer P is of a custom data type with the name class A and pointer to that. So essentially, it will store pointers to the objects of A, of, of the data type A. Okay, so we can do this then. We'll take the address of A and store it in P. Okay, and A itself is an object of data type A. Okay, so P now can store pointers to the pointers to the object of A, because that's how we defined it. Similarly, we can define the pointer Q of data type B. Okay, and I will pass it the address of B. Then let's write something like this. Okay, where we are reassigning classes uh, as such. Let's say, so A is the data type of A, B is of data type capital B. Okay, so any guesses if this will, is this all right, or is this throw an error? Will this throw an error or anything? Okay, so maybe we can, sorry for that. Yeah, okay, so let's compile this. So before that, any guesses? Anybody wants to take? Okay, let's run it and see. This throws an error. The reason is you can't implicitly convert a custom data type of B, which is of data type capital B to a data type of capital A. So small a and small b are the objects, and then their data type is the classes A, capital A and capital B. Okay, so this will throw error. Okay. Then what if we cast it? As in we saw casting before where we use double and such, right? Double integer and such. Can we use casting to convert an object of data type B, capital B, explicitly cast it to capital A? So that is the data type in a way of A, right? And store it to A, small a, the object. Any guesses? Okay, so let's run it and see. Again, this also throws an error. The reason is you cannot even explicitly convert a custom data type from one to another. Okay, so these um, data type conversion as in pointer or implicit explicit casting like this is usually what one can think of like is usually just for the inbuilt data types. Okay, as in when you convert from integer to double and so on and so forth, or double to integer, it has a demotion as in we have to trim off some bits, right? So those kind of rules are already defined for the program, as in for the compiler and such. So those things the compiler will know how to handle. But stuff like this, where you just convert from any custom data type to another custom data type, compiler really has no idea how to handle this. Okay. So again, this will also throw an error. Next, if we take more examples, but like for the this also, can anybody say what will happen? This is pretty much the same example as in line 20. So this also throws an error, okay? Because again, you're converting from A to B, like capital A data type to capital B. Not much of a difference if you're converting from capital B to A also, capital A. Okay, so this also throws an error. For completeness sake, let's write this also. This will throw error again, right? Uh, Pretty much the same example as this. Okay. Next, let's try to, so we see the objects themselves and trying to convert one to another. But what about we if we have take the pointers themselves? So let's say p equals to q. Any guesses what will happen now? The difference is that this time these are pointers. So let's see. Again, you cannot assign uh, this custom data type pointers to one to another implicitly. Okay. So again, this also throws an error. And if you try the opposite also, again, just show it for the completeness. Yeah, same. So not much difference. We convert one to another. Also throw an error. Okay. But what if one casts the pointer as an explicitly cast? So here we try to implicitly cast it. What if one tries to explicitly cast it? Any guesses? So let's run it and see. So it doesn't throw any error, and then you can access the P, essentially how you would have access Q. So here's the important thing. You cannot implicitly cast objects or objects pointers, okay? But you can explicitly cast the pointers. You cannot convert objects explicitly if you like from object in themselves, but the pointer themselves you can. Okay, right. So to drive home why is it so is, let's say A is some object, okay, of data type A, and B is some object of data type capital B. Now the memory that A will be stored, right? How much of memory, how is it going to be stored in the actual RAM or cache or whatever? All that will be different for both capital A and capital B, because they're two different classes. So assigning it one to another really doesn't fit as to how much memory you have to deallocate, or how you're going to destroy it, or then move the new data to that memory. Okay, that the whole logistics of it is not exactly known. If you think about it, what's going to happen if you try to replace another object with another object? Even if you try to explicitly cast it also, the same problem happens. Okay, but when you try to implicitly cast pointers, again, that is not allowed because same, pretty much the same reason. But let's say you explicitly cast it, right? So pointers, always remember, pointers themselves are just, in a way, just integers. They're unsigned long integers, as in the highest integer that can be represented in your system. That is the data type of your pointers. All the pointers have this data type. When we say the uh, data type, so let's say integer A pointer, like we saw here, double pointer Q or integer pointer P. Always remember, this integer or this double is the data type of the value that pointer is pointing to, not the address it stores. Pointer always stores address, and addresses, they're always represented using unsigned long integer, as in the depending on architecture. So it will be 32-bit system, then the addressing will be 32 bits. So whatever maximum a 32-bit number can store, so that's like 2.4 billion something. So that's the maximum value of the address, okay, that your pointer can store. In 64-bit, it's, I think, it's definitely much larger. Okay, so here the important thing to again note is, because P was storing an address and Q was also storing an address, when we cast this address of Q to pointer A to be stored in P, that is, as in the compiler will allow this. You might run into all sorts of issues later, but that's a different thing altogether. But if you think about it, it's essentially like storing an address into another address, which again is a number. It just so happens that this P and Q were not void pointers, they had some data type. Okay. Hence, when you try to explicitly cast that pointer and then store it, compiler just accepts it. Okay. Yes, the address that P had gets overwritten. So the object it was pointing to, right? The A, it no longer points. And very important thing, because we have the ob object A here, when it goes out of scope, uh, its destructor will get called and it will get destroyed. But if P was pointing to some value and now it isn't, and when the program ends, there is no way of destroying that value now if nothing is pointing to it. Okay, so one has to be careful while overwriting pointers like this. Okay, but nonetheless, there can be use cases where you want to do something like this. Okay, uh, for completeness, I'll write another the next line. So essentially, this is casting P to B pointer type and then store it in Q. These both are perfectly valid. Okay, so it's also not throw an error. Fine. Okay. Next is, let's say Right. So yeah, we can convert it and then try to access, let's say, the member variables as we roll those things. So I'll access the value I inside P. So let's do it this way first. Okay. So that points to the value 7, which P has. So P is of A, which is 7. Yeah, 7.0. So maybe let's make it 8. So we'll know which value it is actually pointing to. Okay, 7, as expected. If we access the value B, okay, we see that it prints the value 8, as expected. But now let's do it this way and then print. Yeah, so as you see, it prints 0. Again, the reason for that is you have you have explicitly casted that pointer to A, and now P sees the address of Q. So Q was of type B, remember. Now we're accessing B, okay, through P, treating it as A. So we are treating B as A now. And what value it has or whatever members, it's all up in the air. We have no idea how it's going to behave. Okay. Can cast it, yes, but don't expect it to behave the same exact as A. Okay. Right. Same with probably this also Q. Yeah, it somehow does. But yeah, all right. We can take another example. So let's define the class A again. Public member. Okay. Integer I, same as before. Another class B. Now let's say this time this class is derived from the class A. Okay. Right. Now let's define another public member of class B itself. This time double D. Then integer name. As before, we'll again declare like define an object A of data type capital A. Define an object B of data type capital B. Then we can similarly have pointers. So A capital A pointer, right? Data type. The data type is A, and we define a pointer of it called P and store the address of it. Similar to like what we did before. The data type B and we define Q for the address B. Now define another pointer, a void pointer this time. Okay. And we can do the same exercise. Now remember here, the Slight difference is that previously we had two different classes, okay? Class A and class B, completely different. But this time you're deriving the class B from A. Important thing, here we're deriving the class B from A. So whatever members and everything A has, even B has access to them. Okay. So this is public. So B has access to I, okay, publicly and internally also both. Okay. So that's the important distinction. Now let's say I write P equal to Q this time. Essentially what we did before, all of the same thing will repeat. Okay. But this time we will write the same thing, but this time the only difference is that class B is now derived from class A. Okay. Formatted to look more neater. Now let's say I write this. What do you guys think will happen? Will I get the same error, something different, or no error? Okay, before that, maybe you can do this also. Just say I write this. Essentially what we did before. So let's write A equal to B and see the output. Okay, sorry, my bad. It's okay. All right. Um, right. Can anybody sorry. Yeah. So when we did the same thing before, we it threw an error, but this time it is okay. Like we're writing A equal to B. Can anybody think or tell why is it so? We're writing B equal to A. Let's say you write A equal to B, we wrote, and now let's say that we write B equal to A, but that throws an error. Oh, but if I comment it out, error vanishes. Any guesses? So again, the answer is actually why what the classes A and B represent. A is the base class, B is the derived class from it. So an object of B can be stored inside an object of A, as in if you just overwrite it. Okay, so that is sort of like allowed, but can't do the opposite way. You can't store the base class inside the derived class because right, the base class is derived. The base class is a sort of like from which you derive the derived class, right? So this is allowed, and this is not allowed. So this is where where is like this also. The next thing to do here is yeah. So this one through an order. We saw this through error. So now let's take this example now, where we are storing the pointer of Q, as in the B pointer, into A. Again, any guesses? Okay, let's run it and see. Right, so this also doesn't throw any error for pretty much the same reason, because you're able to, if you're able to write the object of B into the object of A, of data type A, which from which it was derived, right? You can do the same thing for pointers. Okay. The implicit casting here uh, is all right, as in it is it's a valid implicit casting. Okay. So this here Sorry, no error. And given all the information, I guess you guys can guess now. If I write this, then what happens? So as we saw before, this actually should throw an error because you're converting. Yeah, so what it says here, the pointer is incompatible when you're converting to B star from A, the A pointer. Okay, right. So this is not allowed. Okay, so we had the pointer R also. So let's say we write it this way. Write another example where we store R into P. Any guesses what will happen if I run this program? This is okay because any data type pointer can also can you can just store it in the void pointer. This will not throw an error. Okay, that's what we see. And similarly, just for completeness, I'll also write this. This also will not throw any errors. Okay, but what if one does the opposite? So this one I discussed previously also. This will throw an error as we can check this because you cannot implicitly cast some the void pointer to some other data type. Okay. Okay. For completeness, same, but with Q. Okay. So again also throws the same error. Okay. And the final for that, return 0 for complete. Okay. So we saw some examples of typecasting again, where is like similar to previous where we had classes, but this time one class was derived from the other class. Okay. And then how do we store values and variables? As in, if you try to cast them implicitly or explicitly, these will be the results. Okay. Any questions so far? All right. Let's moving on. We'll take one more example. As it will include IOString. Define the same thing again, class A. Okay. Then make a public. Okay. Where it's an integer. Call it data. And let's call it A because it belongs to class A. Okay. Let's define another class B. Okay. And again, we'll make this derived class from A. Okay. So public A. We'll have a public members now. This will be, let's say, the same integer type, but we call this data B. Okay. Let's write the main function. Okay. Now let's define the objects for each of the class. Pretty much the same, similar to what we did before. Okay. So these are the two objects, small and small b, of type capital A and capital B. Okay. Then if I try to access the data member of A, okay. So A is this base class. Okay. It has the data member data A, so I can do A dot data A. Okay. And since this is public, so I'll write it. I'll store value 3 to it. Okay. Next, I'll make um, yeah this yeah. Next, I'll make B. Okay, and B has access to its data member, right? So that will be let's say 8. Its own data member it can access. It can also access because it's a derived class from class A, right? So uh, data A, and that will be value 10. Let's This is allowed because you have the object of B has access to both its data member and its parents data members. Okay. Let's say if we try to compile this, should be all right. Yeah. So far so good, right? And then um, so just to be clear, if A tries to access the data of B, and let's say I store it as some 4, okay? Any guesses? Is that allowed or not allowed? So this is not allowed. Also, you can, yeah, correct. That's correct, Ayush. It's not allowed because it's A doesn't have the data B as the member. It only has data A. Parent class or the base class cannot access the members of its derived classes. Okay, so this is not allowed. Okay. Now let's define pointers to the same objects. Okay, we'll call them PA, pointer A. Okay, and give the address of A. Okay. Similarly, we'll make another pointer B, call it BB, and give it the address of P. To access these values, one can to print them. So let's do it this way. This I'm showcasing how you can access members of an object. Okay, so the object is A and B through their pointers to that object. So the P and PB are the pointers. Okay, so we'll access them with this data. Okay, and so on. We'll make let's complete this. So data will be the first member and in line. So next we can access the pointer B its own data B. Next from B you can also access A. Okay. So as we see, the same values that we stored, we can access them through the pointers and access the data members. Okay. So the arrow operation is essentially to use to access data members through pointers. Essentially, the arrow operation is like dereference. So the uh, this is a pointer, right? So you dereference it and access the actual object. So that's the first thing. So this we saw that last time. Yeah. So you can think the arrow operation as first the star operation, which is the dereference. Here in this case, the dereference is to access the object A, okay, of type A, and then, oh, sorry, and then with that the dot operation, as in accessing the member itself. So the arrow operation here first dereference the pointer. So PA is actually the pointer to the object A. Okay. So first dereference, so the object gets accessed, and then the dot, which is the accessing the member. So both combined is essentially the arrow operation. And we access the data A, okay, the so which is the member. Similarly for the other cases. Okay. Now we saw this before, but we can write it this also. We'll store the address of B, right, which is the derived class, right, to the pointer of A, which is of data type A pointer, as in the base class. Okay, this is allowed. And let's do the same operations again. And this time I'll maybe add another line so that it distinguishes of the new code. Okay, for that. So let's store it this way and then try to print the values. Okay. So it pointed to 3, 8, 10 as usual, but then it pointed to uh, data A as 10, but data B and data A as the correct ones. Okay. I guess you can see why that happened, because the A now actually is pointing to B, as in the PA is now pointing to the object of B. Now the object of B has data B. So when you're trying to access A, it is accessing the uh, data member A. Okay, so hence you get 10. So I hope this is clear, as in why this happened. PA is not pointing to its uh, data anymore, as in it doesn't have, it's not actually accessing 3 anymore, which has data A. It will access the data A, which was stored in B. B is another object. A is another object. A has an data A, right? A has a data, small a has a data A, which was 3. And small b is a derived, is a class, is derived from class B, a class capital B, which also has access to data A. Okay. So its data A, which is 10, is what gets accessed. Okay. All right. Any questions so far? All right. Okay, if there are no questions, maybe I'll start our concept today called cost casting. Let's for an example to understand this. So we'll write a main function where let's say I is storing the value 0. Okay. Now let's say I make uh okay, let's do it this way. Let's say I make a pointer to I, okay, which is ptr, okay, an integer pointer, okay, and give it the address of I. That's perfectly valid. I have I which stores as a 0 or some value. Then let's make it 10. It stores a number or integer 10, and the address of I, okay, which is ampersand I, is what I'm storing in ptr, the pointer, okay, which is an integer pointer. Out of the same thing, I can also do it this way. So integer reference this time, call it ref, okay, and give it heights. Okay. I don't have to uh, pass the address because here ref is a reference. It's not an pointer or anything. So when I write something like this, it means the reference and I are the same thing. As in the reference ref essentially means I itself for all intents for all like purposes. Okay. So the compiler, the code will see wherever I, it will describe I for its code. It will use the same for ref also. Okay. So in perspective of memory, they actually refer to the same location. You can think that way. Okay. And you can print I to check its value. Okay. So let's do that. Alright. Okay, so that prints 10, and all these are valid operations, so it threw no error. Okay, but let's say I instead of these, I make them constant. As in, what does this mean? So we know that if I had constant I equals to let's say 10 or something, instead of just I, it means that the value of I, whatever it stores, is fixed now. It won't change. That's the intent behind const. I need the integer also. Sorry about that. So it's an integer I, but with a const qualifier, it means that you cannot change the value of I later on. Okay. So once it's defined, it's done. That's it. So that's what in the context of um, variables, this is what it means. Okay. Now, if we let's take the original int I, okay, but this time with for pointers and the reference, we'll qualify them with const. So what does this mean even? What it essentially refers to is this is a const pointer, okay, and this is a constant reference, right? So let's say, I mean, it's the idea is pretty much similar to what we see here, but just to take example, if this was the original case, okay, and I write, maybe I'll just do it this way, it's better. Okay, and then print 9. So it prints 9 because the reference is essentially what I is, right? So if I change reference, the ref variable to 9, even I changes. So that's what the print also tells you. Okay, but let's say I do the same here? Any guesses what will happen? Okay. So actually this will throw an error because a const reference to I cannot change its value. So that's what a const qualifier, essentially it's similar to what we see here also. A const value cannot change it. Okay. It's yeah, I think this should be okay. No, it's an error. Okay. Yeah. So let's take the actual integer also. Okay. Question is, oh, sorry, my bad. Um, yeah, let's do it this way. Yeah. So the original I we defined two we defined two variables. Okay. One was an integer pointer, another is an integer reference. In the second example, the same I, we define a const integer pointer, another is a const integer reference. And when you try to change the reference, which is a const reference, that's what will throw an error. Okay. You cannot assign variable ref to a const qualified type. Essentially, that's what the compiler also says to you. Okay. So the idea is that when you const qualify a pointer or a reference, so when you const qualify a variable, you cannot change it. Yes. When you const qualify a reference or a pointer also, you cannot change the value they're referring to. As in, a reference also stores the same value, so you cannot change it. Okay, through reference, you cannot change even the pointer also, as we'll see. Okay, the pointer is also storing pointing to a value, as in pointing to an address, right? And it has some value. You cannot change that through the const pointer. Okay, that is what the const here in this context mean. Let's see if we can const qualify I and then change it. Again, it will also throw an error. You cannot do that. Okay, or there is a difference between having the variable is as const or not, as we'll see. Okay, so let's have this for now. Okay, and call it and name this error. Okay, so to get around this, there is a way where you can change the value of I. Okay, even if the reference or pointer is const qualified. C++ and C both provide a way. Okay, so the C++ way of doing the same thing is const cast. Okay, and then you have to give a template. So the template here is the integer reference. So the integer reference, and the ref is what will pass to it, and then main line. Okay, now this will compile and give you 9. The reason is the reference was const qualified, yes, but temporarily we are treating the reference to be editable. So you can change it. Okay, and it stores 9, and it was pointing to I, so right? So as in I, it was a reference to I. So when you print I, it gives you 9. Okay. Important thing to note is here the const cast was able to change a const reference. Yes, that is true. But there's a slight difference. Let's take another example like this and then try the same. So the difference is that instead of it being I being integer, I made it const. Okay. So let's see if we can do the same. Okay. So this one, yeah, it was not able to change it and did not throw an error. Okay. Um, right. So essentially what I wanted to get at here is you cannot change a value, okay, if it is already const. The actual value I, okay, when it was declared, if it was const, you cannot change it. It actually did not throw even an error also. I guess that is caught in bit caught it's caught and then it just ignores this probably. In any case, if you remove this, the essential idea here is that the original value, if it is not const, you can actually change it. That's true. I mean, if it was not actually declared to be const, you can always change it, right? It just so happens that the reference or the pointer you have are const qualified, as in you cannot directly use them to change it. Okay. You have, if you really want to change them, you have to go about a little roundabout way. You have to use a const cast. Okay. I know that here the uh, naming is little maybe confusing. Here it doesn't cast it to const, but sort of like removes the constness. Okay. Okay. So that's the it might get a little confusion here, but that's the idea here. It removes the constness from the reference. Okay. So it's a point, integer reference. And because the original I, which is it is referring to here, right? It is so it's a constant integer reference I. The original I was editable, so it was able to edit it. So if you run this now, it's all right. It will change to 9 now. Okay. But if the original thing is not editable, as in that itself is const, so then you cannot, even const cast cannot change the value. Okay. So the main takeaway here is that you use const cast to remove the constness of a reference or a pointer. We'll see the pointer example also now, but that's the idea. If the original I itself is editable, then you can remove the constants and edit them. Okay, that is the idea. The other way to do it is you cast it to be integer reference and then store 9 bit. This will be more like a C style way of doing things. C++ has a neat um, syntax for it. So yeah, this is also stored 9. So this is the C way, this is the C++ way. Okay. Correct. So the reference itself, we just cast it as a integer reference and then we are through. Let's say if make it as false, then what happens? Any guesses? Okay, let's now hit and see. 10 as the original value is just 10, right? Even with casting or like a removing the constness, you cannot change that value. Okay. So let's do it this way. Then we can even use the const reference. Okay, let's actually have it to do a const cast, okay, for the pointer. Um, as we saw, this was an error. Okay, so let's do the pointer, then we'll bring all of them together. Let's make this as 9. So previously, just this code where I was 10 and the const reference and const pointer both were defined, and dereferencing that pointer and storing 9 to it. Okay. This will throw an error because this is only read-only variable. So const pointer cannot change its value directly. Okay. So what's the other way? So this is error. So what's the similar to the reference as in removing the constness? What is the other way? You can do this C style way. So cast it as integer pointer. So to remove the constness of it. Okay. And then store 9 to it. Uh, right. So, okay. I see. We cannot directly cast it, the pointer in the same way. Yes, my bad. but with C++ you can. So let's write for. So const cast, okay. So this what did I do there? Right? So oh, my bad. Yeah. So inside the template, okay, similar to how we put sorry in integer reference, right? So here we'll put in cases integer pointer. Okay. And then we pass the reference, right? We just pass the pointer here. But one has to be careful. Here it was defined to be integer reference ref. Okay. So you can think of it like just integer uh, ampersand ref. Then you can store values. If you cast it this way, it becomes integer pointer and then pointer, which is similar to this. You have to store address to it. So let's say if I want to store the value like this is wrong syntax. I have to re-reference it. Okay. That's just a small thing to remember. Okay. And then let's say if we print I, uh, is 9. So const essentially this is const cast. It allows you to safely remove the constness of a pointer or a reference and then edit that value. Again, this is also a key thing. Only if the actual value is not const, only then you can edit the actual value through the pointer or through a reference. Okay. All right. Any questions so far? All right. If you guys have any questions, I can take those. Rest of the topics we can start from the next class.